Greetings, esteemed members of the City Council. I want to thank you for taking the time to meet with me today. I'm actually reporting to you here from sunny New South Wales in Sydney, Australia. Why are we here? Well, what are we facing? You all have asked me to investigate the increasing number of fish kills that we're seeing in our local waterways. Obviously, because fish are dying, there's a lot of concerns that there's danger to swimmers and folks that use the water recreationally, either boating, swimming, etc. There's also obviously been a significant loss in tourism revenue. When you've got a lot of dead fish on the beach, it's not that appealing. People aren't really going to come for a visit. And another point I wanted to raise, I'd assume there'd been an impact on commercial fishing and recreational fishing as well. So that's what's been happening. So what have I found? Well, we decided, obviously, the first place to look was the water. So we tested the water, and the results came back with parts per million of cyanide, well over the recommended safety margins. What is cyanide? Well, it is a toxic compound. It is highly water soluble. It's poison to most organisms in an aquatic environment. It's also poisonous to humans, and it's highly reactive with metals. The structure of cyanide, the cyanide molecule is a carbon atom triple bonded with nitrogen. It forms the functional group, the cyano group, which is also known as a nitrile. The specific cyanide we're going to be looking at today is sodium cyanide. So that is a sodium atom bonded with a carbon atom, then triple bonded to nitrogen. That bonding takes the form of a covalent bond. And as I mentioned, cyanide is hydrophilic. That means it's water-loving, and that's extremely important to what we're talking about here today. First thing I'll get into is the toxicity to fish. The way that the cyanide enters the fish's cells, as I mentioned, it's highly reactive with metal. It actually bonds with the iron atom that is present in the enzyme known as complex 4. That's possible because the iron atom itself has a variable number of electrons on its outer shell. It actually makes it quite easy for other molecules to bond to it. That's actually what's leveraged in a lot of our metabolic and natural processes for both humans and fish. We use that to bond oxygen to the electron transfer chain and produce energy. But what happens here is the cyanide molecule actually hijacks that, and it forms permanent inhibition of the electron transport chain. And so that's no longer able to have oxygen enter the process. It stops producing energy. And when that happens, the result is cell death. And really, any cell that uses oxygen is susceptible to cyanide toxicity. Where this all takes place is inside the mitochondria. That's where the ETC is located. Most cells in humans and fish have mitochondria and leverage the ETC. Interestingly, human blood cells do not have mitochondria. I won't say they're unaffected by cyanide toxicity, but they are not directly affected. Fish red blood cells, on the other hand, do retain functioning mitochondria and therefore are susceptible to cyanide toxicity. I think the easiest way to think about this is the more oxygen the cell or the tissue or the organ uses, the more susceptible it is to cyanide toxicity. Simple examples would include the brain and the heart, obviously critical to survival and function, and those are the most susceptible to cyanide. Well, we know how cyanide gets into the fish cells now and the damage it can do there, but how does it get into the fish itself? There are a couple of ways it's possible. In my opinion, the most likely scenario is that the fish is absorbing the cyanide from the aquatic environment through its gills. I mean, basically, the fish gills are what enables the fish to absorb dissolved oxygen in its environment into its system, so it has access to oxygen. I think this is the most likely contact point for the cyanide. The other scenario, which is much less likely but possible, is that it enters the food chain. The fish consume smaller things that already have cyanide inside them, and it builds up and becomes toxic. The reason I don't think this is likely, well, number one, as I mentioned, cyanide's highly water soluble. It has low persistence in water. So really what that means is the cyanide dissolves in the water and dissipates quickly. Additionally, we're only seeing the fish deaths in the last couple of weeks. And so that leads me to believe it's something new and a little different than a food chain problem. Where do I think it's coming from? I do think the answer here is fairly obvious. We have local mining operations and wastewater treatment operations. Sodium cyanide is heavily used in mining. It's what the miners rely on to remove gold from ore. They spray a cyanide solution on. It basically dissolves the gold, leaches off. The gold is then stripped out of that solution. They spray it back onto the ore. It does it again, and then the ore is completely depleted of gold. But as a result, mining produces a lot of cyanide containing wastewater. And then water treatment. In addition to mining, there's several other industrial processes that leverage cyanide. Typically, the water is sent off to wastewater treatment. Wastewater is treated. They reduce the cyanide to an acceptable level before it's released into the environment. But when we see flooding, sometimes those treatment plants and mining facilities can be overwhelmed, and we see untreated runoff laden with cyanide flowing into the waterways, which I think, as I mentioned, is the most likely scenario here. As we all know, in the last couple of weeks, we've had several major storms. I hate to use the analogy, but it really was a perfect storm. We had a Category 3 hurricane make landfall. That had an associated storm surge of about 8 to 12 feet. And that coincided with the timing of what we call a king tide, which is a very, very high tide. And that storm had an associated rainfall of over 2 inches, so extremely heavy rainfall. What happened is that flooding overwhelmed the wastewater treatment plant. We saw a lot of untreated water flow into the aquatic environment, and additionally the safety mechanisms, the treatment mechanisms at the mining facilities were totally overwhelmed by the volume of water, and we saw untreated runoff from both of those sources. And so I'm fairly confident to say this is how we've arrived at this problem. There is some good news. As I mentioned, cyanide has low persistence in aquatic environments, so I'm not recommending we do this, but if we did nothing with the flooding stopped, we should actually see the fish kills stop, because that cyanide is going to dissipate quickly. It's not being replenished. There's no more runoff, and everything should stop, and we should see water, cyanide levels drop to safety levels for humans and for all the organisms in the aquatic environment. I would say, though, that we want to check the mining facilities and the wastewater treatment for damage, make sure there's not now permanent damage that's resulting in consistent runoff of untreated water from either one of those sources. And finally, for the long term, and we've seen significant decrease in tourism revenue and in commercial and recreational fishing revenue. I think we should ensure this doesn't happen again by retrofitting the mining operation and retrofitting wastewater treatment. So in the event we see another storm or series of storms, we're not faced with this same problem, and I think you can absolutely justify the cost in avoidance of lost revenue from tourism and fishing. So, any questions or concerns, you know how to get in touch with me. I appreciate your time. Thank you very much.